Right, so we'll start off today with a quick reminder of what we were talking about last week, and then we're just going to go through a sequence of code examples introducing the real-time operating system kernel that we're going to be working with. So, quick reminder of what we talked about last week. We're discussing how we want to divide everything into processes, and we're going to use an operating system to tolerate these processes. So it all essentially comes down to multitasking. We spent a bit of time talking about context switching, which is the key operation to take one task out or process out and put in the next one. Right, so a reminder, a process is just a unique execution of an independent activity. So any function of code, you can have multiple instances of the same process, and it's the operating system that manages your processes. We talked about several types of multitasking. The one that we're going to focus on is going to be preemptive multitasking. This is what is used by microCL2. And so this involves essentially, the key part is a timer interrupt which regularly runs an interrupt service routine and allows the operating system to take charge of the CPU and allocate which process goes in next. And as mentioned before, it doesn't need to just be in a timer interrupt. It can be a process going to sleep, or it can be a process pending on some I/O or data or something else. Right. And so in terms of some simple terms, the thing that I wanted to remember is we're using microCL2 and we're calling our processes tasks. And these tasks are actually threads, which are lightweight processes that share memory space, and this can have some issues. Right. So how do you create a task in microCL2? It's a very simple bit of code, just going to walk you through it. First up, every task must have a unique priority. So if you assign multiple tasks the same priority, what's going to happen is your second task just won't be created. So be aware of that. The higher priority task always runs, so it's always going to give the CPU to whatever is the highest priority task at any given time. And note that the higher priority is starting from 0. 0 is the highest priority. We have a system which has 64 tasks, so 64 would be the lowest priority. And the lowest priority task is the idle task, which we actually will talk about probably in tomorrow's lecture. Last time we mentioned that every task has its own stack, so it stores all of the return addresses, all the information it needs, and all of its local variables that it's working with. So every time that every time a context switch happens, it needs to store all its local variables to its stack. In terms of the syntax, this is the syntax. So first up, we say this OS task create, operating system task create, kind of self-explanatory. It returns some error function. Now, you're probably familiar with this. It happens a lot in C code. A lot of your standard functions return errors. So if you've got malloc, a lot of people just say malloc some variable. Really, you should say error equals malloc and then check that you actually allocated your memory. Or similarly, if you had fopen some file, if you're opening some file, again, you want to check it's opened correctly, so you should check the error message. Now, a lot of code tends to just ignore this process, right? You see C code all the time without your error being checked, and really this should be followed with some if error ... Generally, C code will omit it for mallocs, and often the reason is because how often do you not have enough memory in your system for your dynamic memory? Similarly, people forget for file I/O, but that's because how often will your file not open correctly? It's only if your operating system has some lock on it. The reason I make such a big issue of it is, what are the odds of your tasks not being created? Well, actually, they're reasonably high, because you'll do something silly and not realize it. You will assign the same priority to a task. You assign the same priority to a task, it never gets created, you get no error message, your code continues to run, and you go, what the heck has gone wrong? And there's a few other reasons why tasks might go wrong. So just please, when you're doing it with MicroCS2, always check that the task is actually created properly. In terms of other stuff, you have the name of the task as your first argument. Then you have any input data, so actually a pointer to any input data, which is then passed into your task. Every variable has its own stack, which is what we've talked about here. So every task has its own stack, and every task has its own priority, which we've talked about as well. It is worth pointing out, if you want great... Right, so if you want to check any more details on anything that you're creating, on the unit website we have reference manuals. It's more information. It'll give you more details on a lot of things. It will give excessive syntax in times, so just if anyone is interested, you switch to a function which takes as an input a void pointer, where this void pointer is the data that we talked about earlier. Does anyone know why you would use void pointers, by the way? Yeah, so you can use any data type, including any structs. You have a pointer to your struct, or you pointer to the data type. Then you, later on, you tell your code, okay, that pointer is actually a pointer to an int, or it's a pointer to a struct, or something. It just allows the compiler to accept any random parameter being passed into a function. Right, what other things will it say? It will say, note that every task must be written as an infinite loop. Now this might seem a bit unusual or bad coding, but the idea is that we have, our tasks are all recurring periodic processes. We want them to run forever doing their process. The only reason we'd want it to return, well, you can actually kill it, or it can kill itself if you want a one-off task. Just prevent. Right. In terms of the body of what a loop should have, a loop has some infinite loop. We could have a while one instead. And then it must have one of the following services. So these services, essentially what they all do is they all cause some delay. So the ones that we'll use the most will be these two, which says give the delay of one clock tick, or one timer interrupt period. This one says give a delay of hours, minutes, seconds, milliseconds, which you specify. Other ones we'll use later on is mutex or semaphores, which wait on data. So the reason we have these is essentially it allows us to share the CPU. It allows a task to give up the CPU so that we can have this shared processes. Right. Carrying on, got extra information. This is just repeating the stuff that we have. These are the error codes which are pointed out to you, so you can actually use these. In terms of your checking, you want to check if you got no error when you created a task. Or you can check and find out what the actual error is to help you debug. Other random interesting notes, which again, just things you need to be aware of. So task has to have declared task stack type, which will be fine because you just copy code. This one is the more important one, is that there are certain priorities that you can't use because they're reserved by the operating system. And that will cause priority errors here, where you have an invalid priority. Again, if you don't check, you'll have tasks created. You think you create tasks and they haven't actually been created. Right, so on to code. So the code that we're going to walk through is available. By chance, has anyone downloaded this code from the website? Anyone? Has anyone downloaded Microsoft Visual Studio? You can get 2010, it says here. You can also get any other version. Anyone? 2 people. Right. If you really want to learn this code, better than anything else is just to download these examples, hack them around a bit. You'll learn more than what you're learning from me in the lecture, probably, in much shorter time. So if you want to do also cramming your exam revision, I do honestly recommend download this code, run every single example and change a few parameters, get to know the code. It'll help you out a lot. Okay, so let's have a look at them. So when you download, install Visual Studio, you run this program. Visual Studio looks something like this, and you'll get this environment. So point out the important things. So we have the operating system kernel defined here with all of its code. Feel free to look at that if you're interested to understand a bit more detail about what's going on, but you don't really need to focus on that. Similarly, you have this port, this MicroCOS2 port, which is saying mapping the device to specific. So you'll have some porting code for it to go to a NEOS, which is what you're going to use on the lab. Here it's porting it to Win32, which is just a text-based display console thingy. And then the key bit is where you add all your code is in this section app, which you probably can't see at the back, but I'll zoom in as I'm going through it. So in terms of other things, you have recommended config settings here, and you can overwrite them in your local directory. And that's your general code. So the main program, if you're given a chunk of code, which you will when you join some company, they'll say understand how this works, and the way to understand how this works is to look for function main. And main in this case is held in app.c. So what does main do? Can everyone read that? So main, initialize our operating system. You can check that, what that code does in the manual. Critical sections we're going to talk about later, so don't worry about that. It says OS printf. So why does it say OS printf and not printf? Anyone? We talked about printf last time. A little bit. So it's this idea of re-entrancy. So if you have OS printf, it's protected so that it won't be called by multiple processes, and you won't get what we talked about last time was jarbled output. What could also happen is, because printf is much more complicated, you can actually just jam the whole system by having multiple calls to printf, one in a higher priority process coming second. That takes over the printf statement, and you get some odd memory overriding. Right. Then you create your task. Now this task is actually has ext, so it's an extended version of the same thing I talked about. And instead of daring to look at that manual again, it's all basically the same. Define the name, any input variables, some stack space, its priority, and the extra things are just like repeated priority, the size of the stack, the bottom and top of the locations of the stack. That's how you're going to write functions. Then we have this p-error. So p-error takes as an input, it's a function which takes as an input error. So this is what I talked about. Whenever you create a task, run something that is equivalent to p-error. So this is a function that's written in this code. You can just copy this in your own work. What does it do? It takes in an error code and checks if the error code is no error. If it's no error, then you continue. Otherwise, you print out the error code, run a second function, and this second function locks the operating system, which is something that you really probably shouldn't do in general, but it's okay in this case because we've got Windows running below our microCLS2 kernel, so it locks just the microCLS. And then it prints out an error message and stops. Okay, going back to the code, so we've created our task, and then we run OS start. So what this does is, okay, now we're going to run microCLS2, and what happens? Any suggestions? Is there anything left to do? Does it start running at microCLS2 and then I'm done? Because there's no other line of code. Yes, I've already created a task, so this task is going to be run. Okay, what does the task, so it's called start task. Start task is defined in this bit of code. Alright, so start task takes in an argument. This is just a null argument to avoid compiler warning. Right. We print out a couple of statements and then we create task 1. What is task 1? Task 1 says, what does it say? It says print out something and then go to sleep for 500 milliseconds. Right. Then after that, we check that task 1 got created properly, then we continue in this infinite loop of start task, which also prints something and goes to sleep for 1 second. So, given all this run through, this is the first prediction of what should happen. So, just checking it through, in my main code, I write creating start task with priority something. Then start task runs. It says creating a new task. Task 1 runs. It says it prints out something, and then start task at the bottom runs in this loop and prints out something. So who thinks that this is going to be the output when I run this code? You should be able to see that this is not going to be the output just by looking at the first 3 lines. Anyone? Priority is the same. You run with the same priority. What happens? If you run with the same priority, you're going to get some error message to do with same priority. Then I'm going to run the lock code. And this is hideously. I started to run, it prints out, it failed. Press Control-C to exit. Okay, so to fix it, I just changed the priority. So I've changed it to version 2. I changed to version 2, you have task start priority +1. So now, who thinks with version 2, now that I have different priorities, this is what I'm going to get written to the screen? Does everyone agree that it will now write the correct output? Yes? Can anyone suggest why this is wrong? This is wrong. Yeah. this line here, start task will run before task 1, because whereas a function you go straight to task 1 and run the function, with the tasks, because start task is higher priority than task 1, it won't give up the CPU, so it's going to continue running further down the code, and it will output these in the wrong order. And because this is really slow today, I'm not going to show this code running, but you can test it yourself. Okay, so the next version, version 3, I changed the priority to be priority -1. So, with version 3, is this what's going to be printed out to the screen? It will, essentially. So with version 3, what's going to happen if task 1 has a lower priority? That means the second it's created, it takes over the CPU, and then it can run immediately. Then start task will run. They're going to both go to sleep. At this point in time, they both wake up at the same time, but again, because task 1 is the higher priority, it's going to run first, then it's going to go to sleep. Okay, so that's simple enough. Let's run a second example. So to add examples to the project, you just remove an existing item and add the one that's of interest. Okay, so this example is slightly more interesting. First up, so because I haven't edited the main file, what I really want to do is I want to look at start task and see what happens. So start task, like before, it prints out stuff, document the version, and then it creates a task. This time, the difference is the task is being passed in a parameter which is count 0. Okay, so then count 0 is passed into the task. What does the task do? This task says, print out something saying that which is the number the task it is, and then also some timer, some information about how many ticks, which is just the number of clock timer interrupts since the start of the system. And then it goes to sleep for 1 second. So then the second task, so in version 1, it then creates a second task. It inputs count 1 instead as my variable. Count 1 has a value 1, count 0 has a value 0. Runs the exact same process, right? So it runs the same task just with different parameters. And so it's going to print out something as well. Then at the bottom I say, wait, my task start is still running, and then it just goes to sleep indefinitely and really just wastes time. Okay, so given this idea, the idea is that it'll create start task with priority 5, then it creates task priority, first task with priority 6, second task with priority 7, parameter 1. Then what's going to happen is, we've learned our lesson, task start continues running further down the code, so until the lower priority tasks here and here run. Once start task goes to sleep, then task 0 comes into play and prints out its message. Then task 1 prints out its message, and it does it in this order because I've got my priorities 6 and 7 with my parameters 0 and 1. So that's simple enough code, and that works as you expect. what happens if I change my version to version 2? So in version 2, it's the exact same code, same priority, but the difference is that instead of using count 1, I use count 0. So I use the same variable. I pass the same variable into my function, but it should produce the same output because I increment my variable before I run my second task. So, can anyone suggest why the output wouldn't be for version 2 wouldn't be exactly the same as version 1? It's the same problem as what we had from the first task, why it printed out in the wrong order. I can tell you that it won't look like this. If I run it, what it's going to look like is it's going to have zeros there. Can anyone suggest why? Right, so if you think about in the code, we increment my counter, count 0, here, before I run my second task. But when do my tasks actually run? They run once start task goes to sleep. And what's going into these tasks? It's a pointer to a variable. So if you think my 2 tasks are actually starting at this point here, just after it goes to sleep, and I've created 2 tasks which have a pointer to a variable. What is the value of that variable at this point in time? At this point in time, the variable's already been incremented, yes? So if the variable's incremented, the incremented variable goes into both tasks, and so both tasks have the same parameter passed into it. So they're created with the same value. And actually what I said was wrong. They'll both say 1. There'll be no task 0 because it'll be incremented first before it's passed in. Okay, so to fix that, does anyone have any suggestions? I want to I want to get this task, the first task running first, and then I want to create my second task. That's how I could ensure that I increment my variable, and then when the second one's created, it uses an incremented variable. So how do I get my task to run immediately? How can I stop a task running? So yeah, we just talked about it. You can change the priority task. There's 2 ways. You can change the priority or you can get it to go to sleep. So I could just put in here, before I increment my counter, I could type in OS time delay OS time delay 1. That would give a 1 timer tick clock delay. In that timer click, then my process would be created. It's created with my initial value of count. Then the process goes to sleep. I will increment my counter. It will have the new variable count when I create my second task. And I cannot type properly. That's why that didn't work. The other way is to change the priority, which is what we've got in version 3. And so if I define it to be version 3, you notice that instead my task 1 has a priority of -1, i.e. a higher priority than start task. It will pull out start task straight away. It will grab the variable of count. It will run. It will run about with this initial variable. Then it's going to go to sleep. Start task is going to increment my value of count, and I'm going to run. Then it's going to create a second process with the new variable of count. So that will work correctly. The final version which I wanted to ask about is what happens if I put this to version 4. In version So yes, this one works correctly. You'll be able to see if you actually look on a lecture video. It's probably too small there. In version 4, I've got similar code, but now I've got a loop. Now I have this OS time delay before I create each task, and then I'm creating a task, the next task with an increased variable counter. So who can suggest why it won't produce something like this? So what it should do is I'm creating multiple tasks as before. Once I create a task, I increment my counts. So I pass in a different parameter, and it goes to sleep. So it does create the next task immediately. However, as I run further on, something's going to go wrong here. And I'll just run this code just to show it to you. So having a look at this, can anyone work out why? This section here, while you're waiting for it to compile, is basically the key bit of code. They have increasing priorities. But for whatever reason, it's not going to change my value correctly when I print my output. Any ideas? Anything see something suspicious about that code? Something that I've warned you multiple times about over the last 2 lectures. So if you can see, it prints task 0, task 2, task 2, task 0, task 2, task 2, instead of task 0, task 1, task 2, task 0, task 1, task 2. However, right at the start, it does create task 0, task 1, and task 2. So I've got 3 tasks created properly, but task 1 is never running. Can anyone suggest why task 1 wouldn't ever run? So I'll give you a hint, task 1 is running. So task 1 is running, but for some reason it's never actually producing its correct variables. Right. The reason it's slightly hidden is that you're creating a task with a stack, where its stack space is defined at this point. In other words, the stack space for both of your instances are designated the same stack space. So what's happened is you're overriding your stack space when you create the second task. So it's running 2 tasks, but they're sharing the same memory. Therefore, you've lost what you created in your first memory. So again, it's a very subtle bug, but it's something that you need to be able to have a look for and locate. Right. Enough of examples. We'll talk a bit more about operating systems, which will hopefully be a bit more smooth. Right, talking about operating systems. Operating systems, they're your most important resource, function of your computer because it controls all your resources. The most important resource is obviously the CPU, or if you've got multiple cores, which all of your CPUs. Though it also takes control of I/O, whether you give priority to I/O, whether you wait, and it also takes care of shared memory. Make sure you don't allocate too much dynamic memory or if there's not enough space. But the thing that we're going to focus most on is using the CPU and how to schedule your tasks. Right. So first it's worth thinking about process states. So all your processes can be in one of three states, which are either running on the CPU, ready to run on the CPU, or waiting for the CPU. And you should be able to understand roughly how you move between these processes. So going from ready to executing, this is when you schedule a task. When you go from executing to blocked or waiting, this is when you go to sleep or when you wait for some data or some input-output. You'll go from being blocked to being ready when you get your data or when you wake up from your sleep. And this ready will have a queue of ready processes, generally speaking. And the operating system has to choose which one goes next to the CPU. You have a couple of extra paths. You got this path here, which can be a preempt. Can anyone suggest why you would go from executing a process on the CPU for that process to go from there to the ready instead of going via blocked or waiting? I've taught several examples today of why you go from executing to ready. When the operating system finds a higher priority task, so it pulls out the lower priority task and sticks in the higher priority task. The path from blocked to executing is actually pretty rare, and it'll be again when you get your I/O or data, but that'll be depending on the operating system whether it supports such an action. Generally what's going to happen is you'll go through the blocked waiting tasks and then be scheduled to run because it's much easier to deal with. So operating systems have to keep track of priorities, which we talked about a lot. The states, so the states are just these states here. So it needs to know what all its processes are, what's waiting, what's ready, what's blocked. Has to keep track of all its local variables, or what's been controlling your context switches. And processes can be created statically or dynamically during execution. So during today, did we create them statically before they started or dynamically during execution? One question answered. Just guess. Statically. One person has guessed. He has guessed, well, technically, start task was created before we ran our operating system. The other tasks were created dynamically. When the system is running within start task, we're in our microCLC terminal, and we're running our tasks. So you can do it either way. The idea of embedded versus general, again, this is something that we've talked about before. So this microCLC2, which is targeted to embedded systems where you have to meet deadlines. If you meet deadlines, you want to have strict control over priorities. if you want to share your CPU equally, provide fairness, this is what you want in a Windows or Linux environment because you don't want one task hogging your entire CPU. These are just general principles. And yes, so we'll be focusing most on meeting deadlines and about highest priority tasks being taking advantage. We'll talk a bit about other scheduling processes which have different means as well. Just a little bit of notation. The time quanta is a unit time for scheduling. So if you think whenever you're choosing between tasks, the operating system needs a small amount of time to say, okay, this task now gets the CPU. So that is the time quanta. And we'll talk about the rest of this